Welcome back to a course on complex analysis. In the previous lecture, we have just derived the Cauchy integral formula, which is used to evaluate the integral value if we know about the function, right? And an extension of this Cauchy integral formula is also seen, and a few more instances where these ideologies can be applied in problem solving are seen. In this lecture, we are going to see some consequences of the extension of this Cauchy integral formula, right? The first thing that is given to us is if a function is analytic at some point, then the derivative of this function, okay, then its derivatives of all orders, which means with f you can find f prime, then you can find f double prime, f triple prime, and it goes on like this. All these derivatives exist and they are also analytic. This is what we are about to prove in this theorem. Okay, so let us start the proof formally. So we will start with given f is analytic at some point z0. Okay, remember here the choice of the z0 is an arbitrary choice that we will make use, right? So since f is analytic at some point, then there exists a neighborhood of the point, neighborhood of z0, that one we write it as absolute of z minus z0 less than epsilon. Okay, so throughout which this is the neighborhood. In this neighborhood, at all the points, we have the function which is analytic. So that is throughout which f is analytic. So this is what we are saying. How this has happened? This is just because of the definition of analyticity. Okay, in the definition of analyticity, what do we have? We have the function has to be differentiable at some point, not only at that point. In some neighborhood of that point also the function has to be differentiable. Suppose we have the neighborhood. Okay, here we have chosen a particular neighborhood of the z0, that is absolute of z minus z0 less than epsilon. So this is treated as a neighborhood of z0, and we assured by the analyticity that the function is differentiable at all the points in the neighborhood. So all the points in that neighborhood, that neighborhood can be treated as a neighborhood for all the points in the neighborhood itself. So using that, we can say that at all the points of the neighborhood the function is analytic. Okay, next we choose like there is a positively oriented circle c0 centered at z0 with radius epsilon upon 2 such that your f of z, or simply the function f, is analytic on c0 and on the points interior to c0. Okay, because if you just see, if suppose this is your c0 with which you have taken a neighborhood with radius epsilon, next you choose only half of this one and find a circle. The circle we represent as c0. Okay, So inside this neighborhood at all the points the function is analytic. So this is what we assumed in this statement. Okay, if that is so, you have taken a particular circle inside a neighborhood, so the points interior to the circle will bear the analyticity of the function, right, as well as the points on the circle will also give you the analyticity of that function, right? Hence, so when this is true, right, hence sorry, since Z0 is a member of Z0 and the hypothesis of the Cauchy integral formula is satisfied, we have f double prime of z equals 2 factorial, sorry, yeah, if I'm not wrong, I'm right, it's 2 factorial upon 2 pi I integral over c naught f of z, sorry, f of s ds upon z minus z naught to the power 3. This one, sorry, we write it as s minus z. Okay, so this is happening to be true at each point z0 interior to c0, and this existence, the existence of f double prime of z throughout the neighborhood that is absolute of z minus z naught less than epsilon upon 2 gives f prime is analytic at z naught. Okay, so this expression is valid, so with which we just come to this conclusion. And so here what did we prove? We assumed the analyticity of f and we proved the analyticity of f prime, right? So one can apply the analyticity of f prime. Now we have the analyticity of f prime to obtain the analyticity of f double prime, right? So in this fashion we can prove if f is analytic at z naught, then so are its derivatives, which means what? All its derivatives are also analytic at the point z naught. This completes the theorem, right? Next we have something. Okay, this is just a consequence. So we shall write f of z as u of xy plus iota times of v of xy, okay, which is analytic at a point z of xy. This is our assumption. If this is so, then the derivative of f at z, which is ux plus ivx, which is same as that of by the CR equation. This is same as that of Vy minus iota times of Uy is analytic. Okay, with which what we see is that the partial derivatives Ux, Vx, Vy, Uy are basically they are differentiable. So that differentiability will give you the continuity, right? So these are continuous at that point. So proceeding like this, one can easily see f double prime of z is uxx plus ivxx, which is same as that of vyx minus iuyx, or if you want to write it in with respect to y, you can do so, right? So we get like this, f double prime of z is this. So this ensures if f of z is analytic, then all partial derivatives of u and v are continuous. So this is summarized as a corollary here. Let me just read out the corollary. If a function is analytic at some point z, then the component functions, that is what the real and imaginary parts of the analytic function, a complex valued function, will possess a continuous partial derivatives of all orders at that particular point, right? Next, this is called as Morera's theorem, basically. So it depends on the fact that derivative of an analytic function is analytic. So that is what we have just seen in the previous theorem. So using that only, we are about to prove this one. Let us see how to achieve this. So here it is given that f is given to be some continuous function on a domain D, and integral of that function over any closed contour inside the domain has zero value. Then we'll just have to prove this function is analytic throughout D. Okay, so suppose here if you just restrict yourselves to the simply connected domain, this may be treated as the converse part of the Cauchy-Gosar's theorem. Okay, but here it is given to be some domain, it is not given to be simply connected domain. So this result is true for any domain D, whereas your Cauchy's Gosar theorem is just only true for simply connected domain. Okay, let us just proceed. So assume f is continuous on a domain and satisfies integral over c f of z dz equals 0 for every closed contour c in D. Then by the theorem on antiderivatives, there exists an analytic function, or we can, okay, there exists an antiderivative f of z such that f prime of z is f of z with the property that your big f of z is analytic. So we just saw that, just about to use the fact that derivative of an analytic function is analytic. So we just make use of this property to say that f of z is analytic. Okay, so here we are not talking about a particular point. Since the existence of the analyticity of the function big F is throughout the domain D, then its derivative f of z must be analytic throughout the domain D. Okay, this completes the theorem. Right. Next, we have the next consequence. This is called as Cauchy's inequality. Okay, in order to prove this inequality, we need basically few things. That is, first of all, extension of Cauchy integral formula. Okay, let me just write it completely. We need the Cauchy's integral extension of the Cauchy integral formula and ML inequality. So if we have these two things, we can easily prove this Cauchy's inequality. Okay, so these are the requirements. If you are asked to prove, state and prove, if you are asked to prove this Cauchy's inequality in a part C question, you will have to derive extension of Cauchy integral formula, then apply ML inequality to just prove this one. Okay, so hope you people are aware of these things and you know how to present them in exams, but understanding them needs a time. Okay, all you need to do is to pay attention, that's it. Okay, here it is given that f is analytic inside and on a positive oriented circle CR, which is the base assumption of Cauchy integral formula, right? So the circle is centered at z0 and with radius r. Okay, fine, everything is fine. And your function f of z, the analytic function f of z, has the maximum value. That means what? Your absolute of f of z is smaller than or equals mr. This is what you are given. This happens on the circle CR. Then we'll have to just prove fn of nth derivative of this thing is happening to be this one. Okay, so we know that nth derivative of z0 is n factorial upon 2 pi I. Okay, 2 pi I integral over CR f of z upon z minus z0 to the power n plus 1 dz. Right, here what are the things we have here? Absolute of f of z is smaller than or equals mr, and CR is a circle centered at z0 with radius r. So is a circle, is given to be circle, right? So this is the thing that we have. Okay, so let us mark this as equation 1 by 1 and ML inequality. what we can write? We can just write absolute of nth derivative of f at z naught is smaller than or equals, you have this n factorial upon absolute of 2 pi I. So this is there, and for this integral you have the absolute of f of z upon absolute of z minus z naught to the power n plus 1 and length of cr. Okay, so this is what we, and this quantity is n factorial simply upon 2 pi we have, and here this quantity is smaller than or equals mr, and this is r to the power n plus 1. And what is the length of cr? Cr is a circle, right? So which is a circle with radius r, therefore the length is going to be 2 pi r. Your 2 pi and 2 pi gets cancelled, 1 r gets cancelled, and we are just left with the n factorial times of mr upon r to the power n. So this is what we intended to prove in this, and this completes the proof of Cauchy's inequality, right? And we have few problems based on these ideologies. This we will see in the tomorrow's problem solving session. And as for now, I am just moving to the next ideology, that is Liouville's theorem. And this Liouville's theorem states that if a function is an entire function and is bounded in the entire complex plane. So what do we mean by an entire function? This is analytic everywhere on the complex plane. Okay, and this function is also bounded. So by boundedness, this is what we mean, right? With these assumptions, we'll just have to prove this function is constant throughout the plane. So this is what we'll have to prove. So let us start the proof formally. Okay, given f is an entire function. So by entire function we mean that the analyticity is there on C. We can choose any point C naught. Okay, since it is an entire, it is analytic everywhere on C. We can choose okay, in particular choose Fs analytic at Z naught, right? And you can just choose a circle. We again choose a circle around Z naught with radius r, and this can be however large, right? Now using Cauchy's inequality, what we are about to have, absolute of fn of z naught smaller than or equals mr upon r to the power n, where absolute of f of z is smaller than or equals mr. So this has to be the condition, right? So this is that. Okay, now by boundedness of the function f of z, there exists a non-negative real value such that absolute of f of z is smaller than or equals m. So this m is some here what I trying to say is this mr is some constant, some real value which satisfies this condition. But here you do not have the assurance that mr is the upper bound of f of z. Okay, when you just make a comparison of these two things, you can very well see that the constant, observe that the constant mr is smaller than or equals m. This mr cannot be bigger than or equals m, because by the boundedness we have identified this m such that it is the upper bound. Okay, m is the upper bound. Suppose if you have some bound for f of c, that can be either smaller or equal to that m only. Okay, so in particular if we choose n to be equal to 1 in let me mark this as equation 1. So we are going to choose n to be equal to 1 in equation 1. Then what we have is absolute of f prime of z naught is smaller than or equals mr upon r. So and we have just proved this mr cannot exceed m. So this is what we are saying. And initially we have told that this r, the radius r can be however large. Okay, since the choice of r is arbitrary, and it can be however large, what we have is absolute of f prime of z naught is equal to 0, and since the choice of z naught was arbitrary, we get f prime of z is equal to 0 on entire c. So if a function, if the derivative of the function is 0, okay, that is the absolute value of the derivative of the function is completely 0 on c, this means your f prime of z is equal to 0 for all z in c. This clearly tells us that f of z is constant, and this completes the proof. In the upcoming lecture, we are going to see few more important results on complex analysis, that is the fundamental theorem of algebra and maximum modulus principle. So that is going to be the topic for our next lecture. But before that, we will see problem solving sessions on the topics that we have covered. Thank you.